Hello and welcome to today's webinar presented by della Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is AISC 360 2022 Steel Connection Design Updates in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Baca and Siska Cho will be your moderators, answering any questions you may have. They're both support engineers, also located in our Philadelphia office. We always want to encourage everyone to ask questions throughout this presentation. You can do so within the GoToWebinar dialog box as shown here. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So regarding the content over the next hour today, I do want to give a brief introduction to the steel joints add-on for connection design within our program RFEM 6. We'll talk about several of the new features and design options available, and then we'll move on to our examples. The first one will be a steel carport. We'll go ahead and design several different connections showcasing some of those new features. Our second example is going to be this steel platform shown over here on the right-hand side. So throughout these two examples, we'll talk about the connection component and data input. Of course, we'll run the calculation and take a look at the analysis and design results as well. So for those of you joining today that are not familiar with our program RFEM, we do work with this add-on concept. So RFEM is the base program. This allows us to fully model our structure, whether it's steel or some other material type. We can integrate with BIM software and we can get a full static analysis. But when we want to carry out the design of our steel members according to the AISC or the CSA standard, we will need the additional steel design add-on. Now, the steel joints add-on is going to allow us to carry out the connection design within the main program RFEM 6, and that's primarily what our focus will be on today. We also have the structure stability add-on, so this is applicable to both members and connections. To carry an eigenvalue buckling analysis, we can take a look at the different buckling mode shapes and critical load factors, and this is also applicable for connections. So we'll give a brief introduction to the steel joints add-on. Now, I'll preface that this will be very quick just for what we have time for today, but there is a previous webinar that is linked here in the PowerPoint that will go into a little bit more detail of the basic functions within this add-on for new users. So you can certainly refer to that here. The PowerPoint is available in the chat today. We had an issue uploading it to GoToWebinar, so you'll find that download link within the GoToWebinar chat. So in summary though, the steel joints add-on utilizes what we call the component-based finite element method. And this creates this automatic nonlinear submodel generation for every connection that we're defining within the program. So why this is a benefit is because it allows for the design of unique and non-standard connections. We're not just limited to standard connections that other analytical connection design programs will only allow for, but really you can dream of any connection. The bolts and the welds are designed according to the AISC 360 standard, while the plate elements are code independent, but they're designed to the plastic strain limit. Now, as mentioned, the buckling analysis is also available where we can take a look at the failure buckling modes and the critical load factors and determine where we maybe need to apply stiffener plates. So we might be wondering, what are the benefits of this particular add-on over other connection design programs? So within the RFEM 6 della Center, we have access to an extensive library with standard connection components. This means that if we do have a pretty basic connection, we can always go to our library and insert in these components automatically to apply to our model. But we can always build up our own non-standard connection type as well with individual components. We'll certainly see that these two options in our examples today. We can save that then to our library for future RFEM use. We really pride ourselves in having a transparent output of our design checks. So within the welds and the bolts, for example, as you can see over here on the right-hand side, you can see a line-by-line output of the code equations, the code references, and ultimately how we determine that design ratio. But even more so, you can actually download the submodel that we've generated underneath the hood for this connection and open it up like we would any other RFEM model. We can also calculate the true connection stiffness, so the axial and rotational stiffness of this connection, and we now have the ability to automatically export this stiffness back out to the global model in RFEM for the member end fixity. And finally, this leads to the design of the members and the connections in one file. We no longer have to export out member end forces to a third-party program every time the model updates. We have to re-export out those forces, but rather everything is working together again in one file. So we'll move on to our first example, where I first want to go over a few new features that we have implemented within the Steel Joints add-on. The first is going to be a new component called base plate. And this is for, of course, base plate design for foundation connections. We released this earlier this year according to the AISC. So it allows for the design of the base plate connection with the cast and anchors. And what we'll see with our design output is the design of not only the plates, but also the welds, the anchors, and we have that steel to concrete interaction. We've also added the ability to define circular bolt or anchor layouts. So this is applicable here for base plate anchors, especially for round HSS members. We can go ahead and arrange those bolts in a circular fashion here directly on the base plate. Now you'll notice that these have links directly to our website as well. This is also integrated within that PDF handout. The third new component that we'll discuss here is the type rib. So this allows us to quickly define multiple longitudinal ribs on a member plate. So you can see here we could apply this to a web member of an I-beam, for example. It could also be applied to a circular hollow section, which is what we'll see in our example today. We have the ability to automatically specify the welds based on reference objects, so quite user-friendly in terms of defining this new component type rib. We can also transfer shear forces in our base plate design with a new shear lug. So if we don't necessarily want the anchors to take on all of that shear, we can define here a shear lug, which might be quite common for that shear transfer between the column and the concrete foundation for high horizontal or lateral loads. As far as the shear lug itself, we can define here a flat bar or standardized or parametric type section available in the RFEM library. The shear lug can be placed at the center of the base plate or at an eccentricity. Okay, so we'll go to the program RFEM here to begin our first example. So before we begin, we are in our base data dialog box. This would be the initial dialog box when we create a new model, and under the second tab are all of the various add-ons that we have available in addition to the base program. And for this initial example, we do want to activate here this steel joints add-on. So jumping to the fourth tab, this is where we can set our standard. You can see here the AISC 360, the latest 2022 is available here. So now we're within the main program RFEM, where I have already taken the liberty here to model this general steel structure. And this might be some type of carport where we have our columns supporting the steel structure up here at the front, but maybe in the rear, you'll notice some nodal supports here. Maybe this carport is attached to an existing building, such as a concrete wall. And just general AISC cross sections as well as materials have been applied here. So we'll take a quick look at the loads as well. So you'll notice that I'll display our dead load. And if I right click here to display separately, this has just been an area load that has been applied through the load wizard over here in our navigator, where I can also right click to display separately to see those loads applied to the members based on their tributary area. A couple point loads as well for this particular load case. Snow load, same concept here, just an area load. And then you'll also see here a couple of wind loads. So these have been applied to these nodes that appear to be kind of floating out in space here just to define the wind plane in both the X and the Y directions. But again, using this load wizard, we have applied this load to an empty or an open structure. So we want it to only be applied to the cross-sectional area of these members themselves. And again, we can right-click to display these loads separately for wind in the X and wind in the Y. All of these loads are combined according to the ASCE 7. We can see them displayed together here and taking into consideration the factored load combinations. So now that we have done a quick model review, we want to begin with our first connection. So because we have enabled the steel joints add-on, we have a folder option over here to specify our first steel joint by right-clicking and creating a new definition type here. So the first thing to do in this dialog box is to select the nodes, and we want to go ahead and do a base plate design. And we'll select the node at the base of the column, but if we want to do an identical design at the base of the second column, we can select both nodes at once. They don't necessarily need to be defined separately here. So you can see that the program inputs in the members. For this one, we only have one vertical member. We'll call this one the columns. Under the members tab, again, we just see those vertical members and the relevant cross sections and materials brought in. Under the third tab, this is where we begin to build up this connection. So we will insert in a new component here from our component library. And one of the new features mentioned in the PowerPoint is going to be a base plate. So when we insert in this component, we see it shown graphically here, but all of the information at the bottom will need to be revised to account for different materials and different geometry that we want to make for this particular connection. So we'll begin here with the base plate itself. We want to select the steel material A36 that's already been defined here within the model. If we needed to, though, we could always visit our material library within RFEM. So we access the material library here. We use our filters over on the left to filter to AISC, and we see all of the relevant steel materials if they haven't already been defined. But in this case, it has, so we can simply select it from our drop-down box here. Now, rather than a rectangle, we want to modify this to a circle. And the thickness of our plate will be 0.5 inches. The diameter will remain at 10 inches. And then we're ready to jump down here to our concrete block. So the concrete block material is 4,000 PSI. The thickness is going to be modified to 18 inches. Now, rather than defining offsets, I'm going to toggle this to defining the dimensions and position directly. So this way I can set the width here to 24 inches. The height will also be 24 inches. We can set an eccentricity, but we'll go ahead and set this at 0. Now notice we also have the ability to turn on or off if the concrete is to be considered cracked. And with the cracked concrete, this is just going to affect the modification factors that will be used in our design of our anchor, specifically for anchor concrete breakout. We'll go ahead and leave this cracked for today. Now we also have here the grout that we could turn on or off if we had a grout layer in between the plate and the concrete block. Under the shear transfer, so using this drop down, we can select our new option here to define a shear lug. Now, additionally, I could specify if I wanted to consider friction under the base plate. So if I wanted that base plate to take some of the shear forces, otherwise, if I leave this unchecked, we'll see most of the shear forces within the shear lug itself. So as far as the material for the shear lug, we want to select A36, again, available in our dropdown, and we do need to define here a new cross section. So we visit our cross-section library and we can see the relevant cross-sections available for a shear lug definition, including a flat bar. So for this, we can simply input the geometry width of 6 inches. The depth or the thickness will be 0.5 inches, and we can click OK. So now we see the display of that shear lug graphically here within our base plate. The length is going to be modified to 4 inches. If I wanted to rotate this or to set an eccentricity, that's also possible here. And then we have our anchors. So for the anchor dropdown, we have the common sizes, including grade 36 here. I'll go ahead and leave the diameter at 1/2 inch. The first input for the anchors is to define the total number of rows that we have. So we just want one row at the exterior of this base plate. The spacing, though, you'll notice we have an issue where it's colliding here with the wall of our HSS member. So therefore, we want to modify the radius to 4 inches. And now we see that anchor move outside that area. Instead of a total number of 4, we're going to increase this to 5, and the program will automatically space these evenly around the circumference here of the base plate itself. So that all looks good. We want to define whether the shear plane is located in the thread or not. We can go ahead and uncheck this for today. And we can also modify the effective length of the anchors themselves if we'd like to 8 inches. And finally, we have the ability here to define the throat thickness. This would be the weld from the HSS to the base plate itself. And we'll go ahead and set this as 0.177 inches. A nice trick in the program is if I hit the down arrow key and I just simply hit F8, that's going to copy the cell above into the current cell. So that might just be a nice quick time saver for you as well. Now we want to insert in another component here to this connection type, and this is where we're going to take advantage of this new component rib that we also mentioned in the PowerPoint. The stiffen object is going to be the member plate, and within our dropdown, we want to select the column wall. The type of reference is also going to be a plate, and we want the reference to be the base plate itself, that circular base plate. And we see here that that first rib was automatically generated, but clearly we need to make some modifications here to the geometry and the placement. So we want to create these ribs, and you'll notice the default here is to set this on both sides of the HSS. Well, we only want to set this on the front side, so we'll go ahead and make that change here. And we want a total number of 5 ribs. And the program will create the 5 ribs, but again, we have conflict here with the location of our anchor bolts. So we'll go ahead and set the first angle at 36 degrees. And if I just simply hit enter, the program's intelligent enough, again, to space those ribs out evenly between these anchors. Now, the plate element would be, again, a 36 for this rib. We could modify here the thickness to 0.25 inches. And rather than being a parallel rib, we can use our dropdown to change this to inclined. And with the inclined, we see the geometry update graphically, but we need to modify the width to 4 inches. The height will be set to 2 inches. And then we have the indentation of the stiffened component. We're going to modify this to 0.75 inches, and the reference indentation is going to be 1.25 inches. And finally, our last input here is going to be our weld throat thickness. We'll modify this to 0.177 inches. Again, using that F8 key, we'll go ahead and copy that down to the second cell here. So that will be all that is needed for this first connection design of our base plate. Again, we could save this to our user-defined library and always reference it at a later time for a future RFEM model. But going into the graphical display here, back into RFEM in the global view, we can control whether we're seeing these connections globally here in the graphical view with this button in the upper right-hand corner. So currently I have this set to no joint model, but we can toggle this down to a detailed joint model. And sure enough, what we're going to see here is the display of the base plate that we have just defined. Now you'll notice the nodal support's a little bit in the way. Of course, we need this for the global analysis of our members, but we can always toggle this off graphically if we don't want to display that here. Okay, so we want to now move on to additional connection types here. And I'm going to go back to the PowerPoint to explain a couple more new features. So another new component is called fastener with anchor in the concrete block. So the fastener we've had for quite some time, but we now have the ability to fasten these steel members into a concrete block. Now this might look familiar, like it's similar to a base plate, but this can also be used for connecting a steel member to a concrete wall, for example. And that's maybe similar to what we have with our example today, where we want to connect this carport to an existing building. Maybe that's a concrete wall. We also have a new component called contact. So this is in the situation that we have the connection of two members, but not through fasteners. Rather, the top beam is just simply resting on the bottom beam. So what we need to do with this new component type is to consider the nonlinear pressure contact between the two parallel plates and member plates, meaning that in uplift, we want this connection to fail, but in downward compression, we would expect this top beam to bear on the bottom beam. There's also the optional consideration for friction between the two surfaces for those shear loads acting on this connection type. So we'll go ahead and jump back to the RFEM model here to talk a little bit more about these two different connections. So you'll notice that I have already defined here that new fastener connection type that will be essentially bolting this channel member to the concrete wall. So let us take a look at this definition type here. So this is for nodes 21 and 22. Now, in this case, I could not define the nodes together in one definition type because they share the same member. So we'll have to create two separate definitions, but it may be worthwhile to define here the first connection at node 21, and then using our button in the lower left-hand corner here, you can make a complete copy of a connection and then just make minor changes to the geometry for node number 22. Now, what typically would be brought in here is also this transverse member, but I'm not interested in designing this for the connection, so I can simply uncheck it here. And now we just have our single member that is listed here under the second tab, member number 2. Under the third tab is our components. So we would insert in a new component of the type fastener, which I've already went ahead and done so here. We are going to reference component number 1 to the member plate. So this is going to be the web here of our channel. The second component is going to be a new concrete block, and that's what you're seeing behind the member shown here graphically. And the concrete block should look very similar to what we just saw with the base plate. We define here the material, the thickness, the width, is it cracked, does it have that grout layer, and so on. Now we also have the shear transfer. As I mentioned, we can consider friction here if we wanted to. And then ultimately we're going to also place the anchors. So I have 2 rows and 2 columns here of anchors, both in the longitudinal and transverse directions. We set the spacing based on the member end. So you can see here the first spacing is set at 256 inches because it's referencing the end of the member on the left-hand side. So once we have all of this information input for our connection on the right, again, we could just make a copy of that and just modify maybe the offset, a location here of these elements for the left side of our member. So now that this connection is complete, we see them again displayed graphically back here in RFEM. We will create a new connection type while we're within this dialog box. So for this one, we want to graphically select here this node that is shared between this top beam resting on this HSS member. So I can graphically select that commonly shared node, number 9. Well, when I do this, you'll notice that graphically, I see all 4 of these members. So I did have to break apart these members into smaller segments, but that's no problem for the connection design. Under the members tab, we just want to make sure that we toggle this rather than being of the type ended, that it's of the type continuous. So that will tell the program that it will detect that this is one continuous member at the top and one continuous member at the bottom. Now, you'll also notice here the supported ends. So it's important to understand that we are generating this FEA submodel underneath the hood. It is completely separate from our model here in RFEM. So therefore, we're going to extract out these members, but in order for it to be in equilibrium, of course, we have to support at least one of these members. So in this case, I'm going to support member number 3 here. And finally, we're going to visit our components. So for this one, I'm going to create a new component, and we have the new type here called contact. So when I input in this information, this should be pretty straightforward, not too much information to input down here at the bottom. Our first component in contact is going to be set to the member plate. And within my second dropdown, you'll notice that the program will go ahead and highlight here exactly the elements that I want to consider within the dropdown. So we want to choose here all the way down closer to the bottom. We would like to choose member 2 or 3, flange 2. Again, we can see that highlighted here. The second component is also going to be a member plate, but this time it's going to be members 1 and 4 and flange number 1. And again, what the program is going to do with that submodel is to create that nonlinear contact behavior all automatically underneath the hood, considering that this member is resting on the HSS element itself. Now, if we wanted to consider friction for those shear forces, we could go ahead and activate that and input in our friction coefficient here as well. All right, so we will want to move on now that we have this final connection here that we've defined to our last connection type that has already been modeled here. So let me go back to the PowerPoint to explain a few more new features. The next new component is called stub. So this allows us to extend a member with another stub member. And we can connect this member based on an offset from a reference member, give it a length here. And the stub member doesn't necessarily have to have the same cross-section or material. It could be completely different. We also have AISC through bolts. So this is the design of through bolts. This might be quite common in a hollow structural section, as you see over here on the right-hand side. When we're talking about the design of these particular through bolts, according to AISC, we'll check the load-bearing capacity and the tear-out resistance as well. So going back to the RFEM model, once again, we can see that this connection has already been defined here. So we'll just quickly go through some of the elements. Under the components here, you'll see the new component type called stub. So we could find that here in our library. Here's the new stub component. And with this, we will just simply define our material of our stub member. In this case, it's going to be A992. The cross section is a W6x9, but we can always define here a new cross section directly from the RFEM library. We would want to also specify the length here, and then that stub member is created. Now, what's nice is that you'll also notice these plate elements and these bolts that are defined here. This is all done within the same component. I don't have to define here new components for the plates, but rather you'll notice my plate is set to A572 grade 50 material. I give it a thickness, I give it the dimensions, and then my second plate can be set to identical as the first plate. We also have defined here the A325 bolts passing through these plates, as well as our welds and our throat thickness. And by the way, I also wanted to mention that the weld type is also available here in this dropdown. The default is the fillet weld, but we also have here a couple other weld types like the butt weld available too. So that's that stub component, and that's really all that's needed to connect this column to this HSS beam. Now, if I rotate this connection around, and I'll go ahead and turn this into a transparent view, we have a few additional components defined here. And the first is the fin plate. So we have a fin plate at the left and the fin plate at the right. Again, we're just giving it a material, the thickness, the dimensions, and telling the program where it's attached to. We don't have any anchors defined within or bolts defined within this particular fin plate. Instead, we define a new fastener component from our library. And this allows me to specify here that both the fin plate and the wall of my HSS should be connected to the adjacent one with the bolts that I have designated here. So we have just one row here, but we have 2 bolts located in the vertical direction. We give it the spacing and so on. So we can see those through bolts passing here. And finally, we have our welds that will connect the fin plate directly to the HSS element. Okay, so now that we have all of these connections defined, we're ready to run our calculation. And before we get into the results too far, we're going back to the PowerPoint yet again to talk about a couple new features related to the calculation and the results we're about to review. The first one is the life cycle of design results. So this is actually available with all of our add-ons, our design add-ons now. And this is really nice because if we make any small changes to the model, and this is regardless of design properties or settings or geometry or whatever it may be, if we don't make modifications to a specific connection, then those results will not be deleted. So what I mean by this is that we have two connections in our model and we've already run the calculation, we can go ahead and make modifications to one of the connections and the geometry without deleting the results of the other connection. So this will be a big time saver when you are running those calculations for something like the steel joints. So again, the recalculation will apply to the invalid design results only, but the previously calculated results that are still valid will remain within our results available to us in the program. We also can view the graphical display of contact stresses for base plates. So we'll see in just a minute how we can now display those contact stresses shown graphically as you've seen here on the right-hand side. Okay, so we will go back to the RFEM model and we're now again ready to run the calculation. So we jump down to the steel joint design within our table. And the first tab here is our design situation. So this is just our factored load combinations that we tell the program, okay, we want to carry out the strength limit state design according to LRFD. The objects to design, we are going to design all connections that we have defined here. But under the third tab, this lists each individual load combination 1 through 10. And notice that you have the ability to uncheck load combinations. We are generating this submodel underneath the hood, and we are going to rerun each of these submodels through all load combinations. So it's highly recommended if you know some of these load combinations are not controlling, then to certainly uncheck them here so that we're not rerunning them in the submodel, taking up more calculation time. You also have the ability in this additional column to exclude certain joints from the calculation. So for example, load combinations 9 and 10, if I wanted to exclude joints number 4 and 5, but still run this load combination for the rest of the connections, I can do so. Same thing maybe with load combination number 10 here. The other thing to point out before we run this calculation is if we go into the global settings here within the table, you see this new life cycle of results. So we want to ensure that this is turned off. This way we can make these modifications to specific connections without affecting the results of other connections that where the results are still valid. So this is, again, that new life cycle of results. We want to make sure that that is unchecked. All right, so now we will drop to an already saved model so that we don't need to wait for this calculation to run. And when that is complete, we again are down here in our table format viewing the steel joint design and the stress strain analysis. And for each one of these connections, we can view the design ratios by node. So for our base plate, for example, we're going to see all of the design checks for our plates, our shear lugs, our anchors, fillet welds, and the concrete block itself. So if we zoom in here just to take a little bit of a closer look, with each one of these design checks as well, we can always access what we call the design check details. And I mentioned this a little bit earlier in the PowerPoint. So this is going to give us the ability here to take a look at the design checks of the shear lug, for example, line by line with the formulas given to us here, along with the code references. And down here at the bottom is going to be the controlling design ratio based on all of these checks. So again, a lot of transparency here and trying to understand where these design ratios are calculated from for each one of these elements here. Now, we also have access to what we call that submodel. This is just a graphical view of that submodel that's created. So we can see here the FE mesh. Again, everything's kind of happening underneath the hood here. We have the applied member end forces for this particular load combination. And under this second tab, we're currently viewing the plastic strain. So not really much going on here, but we can toggle this to the equivalent stress. So we might be interested in seeing the higher stress points of this connection, wherever that may be. In this case, it's around the shear lug. I also mentioned in the PowerPoint the ability to view that new contact stress directly on the base plate itself. So we can toggle on the effective area, 0.53 square feet, or we can just view the contact stresses directly here along with our color format over on the right-hand side. Now, we also have the option for this particular model to save it to our computer. So I mentioned this also in the PowerPoint that you can save this model and open it up like any other RFEM model. So we'll go ahead and just take a quick look at what this base plate design looks like underneath the hood. So when you open up this saved connection, this is going to replicate all of our connection components. Everything is a nonlinear material. We have a lot of geometric nonlinearities as well that are taken into consideration, but all of the bolts, the welds, the plate elements are modeled with the relevant FE mesh size, again, all underneath the hood. You can see here the member end forces through each one of these load combinations that the program is running through in order to come up with that design. So again, just a nice useful feature if you are interested in pulling up that submodel. Now, the results are also available here under the steel joint design, of course, for our other connection types that you could take a look at here. All right, we will now move on to our second example by going back to the PowerPoint to discuss yet again some new features here. So for our second example, we want to take a look at our new connection library in the Duluth Center. So we previously had the connection library, but it was integrated directly in the add-on. So we just simply migrated that to what we call our Duluth Center. So this just gave us better filter options, and we continue to add on to the options available here. Now, we can directly access the library from the add-on to assign these predefined connections to nodes, and we'll just see how those components then come in automatically. We can make short changes, small changes to them, and that will be a little bit more time efficient. As also mentioned, you can save any connection under your user-defined connections located also within the library. New as of this week, we now have the ability to export a 3D DXF from the steel joints. So this is very exciting as well. You can generate a DXF file from the connection geometry. And with this, 3D line models will be generated for each of these elements. Then it's possible to open up this DXF, of course, in something like AutoCAD, but also other programs like Tekla. Tekla can accept maybe like a background layer of a DXF, so this will be helpful in kind of integrating RFEM with those other BIM type programs. And finally, we have the joint structure interaction. So we touched on this topic earlier, but we have the ability to automatically calculate the connection stiffness. We've had that for quite some time within this add-on, but what's new is that we have the ability to automatically consider the joint structure interaction, where we will take the stiffness properties of this connection, we're going to export them back out to the global model, and these are now going to be new member hinges for our actual member analysis and design. So we're typically used to something being fully fixed or fully released with our member hinges. Well, now we can account for the true connection stiffness for the members themselves. So we will go into RFEM for our second example today. We'll go ahead and pull it up here. And I will begin once again in the base data dialog box. So taking a look at this dialog box and under the second tab, again, we've activated the steel joints add-on, but I've also activated the steel design. So this is for the connection design. This is going to be for the member design. And under the third tab, we can set the AISC 360, the latest 2022 standard, relevant for the member design, but we can still carry out the connection design, again, all in one file. So we will do a quick model review here. This is just a simple steel platform. Again, AISC cross sections, materials are all defined. you'll notice that these transverse members, these have a symbol shown here to represent the member hinge that has been defined. If I double click on this, we see the hinge definition turned on here, because by default, everything's considered fully fixed unless we activate this hinge. And in this case, I did just apply a simple moment release. So you can see here the 3 degrees in translation, 3 degrees in rotation, and I've released the rotation about the member's local Y and local Z axes. Now, as far as our moment frame in the X plane here, everything is considered fully fixed. So this column connecting to this beam, connecting to this column, again, no hinges defined. Everything is completely rigid here. Taking a look at the loads, pretty similar to our last example. We can display this area load. We have our dead load. Of course, we can right click to display this separately, and we can turn that back off for just a general area load. Graphical look, we have live load. We do have wind in the X, again, taking a look at these loads displayed separately here. And then we also have wind in the Y direction. So pretty basic loads. Now we have combined these according to the AISC 7. So you can see in our drop-down box here, we have our factored load combinations, combining all of these loads. And then we also have our unfactored load combinations in red here. So again, we combine all of the loads with the relevant factors from the AISC 7. Now, before we move on to our connection, I actually want to carry out the design of some of these members themselves. So I jumped down to the Steel Design add-on, and let's take a look at our input data. So we have here our 2 design situations that just group together our factored load combinations. We want this set to an LRFD strength design. And then we're also going to carry out the serviceability design for deflection checks based on our unfactored load combinations from this second design situation. Under the objects to design, I'm only going to design these 4 columns. So I've just graphically selected them here. I'm not designing any of the other members at this point in time. So when we run this calculation, we do get the results immediately shown here. And this is an overall envelope summary here of our 4 columns for our strength limit state design and our serviceability. It's worth mentioning too that very similar to the connection design with the member design, we also have access here to our design check details, where you can see all of these formulas line by line and ultimately how that design ratio was also calculated according to the AISC. So very transparent there as well. Now we're kind of assuming that maybe for this steel platform, it's holding some type of very sensitive mechanical equipment, and serviceability is really going to control here. So we've set our limiting deflection ratio to something very, very low, but we can see that overall these 4 columns are still passing even for serviceability, right below the design ratio of 1.0. So everything looks good here. So we now want to move forward with our connection design. And I'm going to go back to my navigator over here on the left. And again, very similar to example number 1, we have here the types for steel joints, where we can right click and create a new definition type. So we want to select the 4 nodes here at the top of our moment frame. And notice that I'm grouping these all together because they are identical connections. So this brings in all of the members at these particular locations. Well, the first members here, we can rename this one to columns. And then our second set of members that are brought in, these are going to be our beams. Now, for the transverse members, I'm actually going to turn these off. I'm not interested in designing them for my connection. Same thing with my X braces. So notice we'll just kind of turn those off altogether. I'm only interested in designing this moment connection here from the beam to the column. Well, down at the bottom, we have what's called here our stiffness analysis configuration. And within this dropdown, we have the ability to create a new configuration or edit the existing configuration that's here in the model. And if we take a look at this definition type, this allows me to automatically calculate the stiffness of this connection. Now, this first configuration, notice I have the joint structure interaction turned off. This is just simply going to give me the stiffness values once I carry out the connection design. But the second configuration has this option turned on. This means that it's going to export out the stiffnesses as new member hinges in my global RFEM model. And that's actually what we want to use today. I'm going to use my dropdown for that joint structure interaction to take place all automatically. So under my second tab here are my members. I have my columns. Again, we want to at least set one of these members to supported. But this is where I can set the stiffness analysis. So in this dropdown, I can say, okay, let's go ahead and calculate the stiffness, not only for the axial, but also the rotation if we wanted, MX and MY and MZ. So we can go ahead and turn those on. No need to do it for the beams. We're just going to do it for the columns here. So once we have this information input, we're ready to jump to our components. And this is where I want to take advantage here of our library and to show you how we have moved this to the Delubal Center. So within our library, you can see all of the various options that we have for pretty standard connections, including base plates, but then we get into our member connections. We can utilize our filters over on the left. Notice our user-defined filter is also available here for any connections that we've created ourselves and want to access later. So for this case, I want to access or to set this filter to 2 members total. And I can scroll down here and I'd like to select connection number 84. So when I have the connection type that I'd like to apply to my model, I'll go ahead and click OK. And what this is going to do is to take all of these components that have already been defined and apply it to my model. And so we see this come in, and this certainly does not look great. Well, this is a quick fix here. We just need to reverse here what's the beams and what's the columns. So we'll go ahead and use our drop-down options here. And now those elements, those components have been applied here to the model. Now, of course, we need to make some changes. The geometry doesn't look great, and we'll go ahead and do that now. You can set the materials of all of these elements directly here, or we could individually do it once we get into the various components. But again, all of these components are already defined here automatically from that library. So what we want to begin with first is this top stiffener. And I'm actually just going to delete this altogether. So this is the advantage of using the libraries. We can pull in these components, but we can make any changes we want, including adding new components. And in this case, I'm going to add a new cap plate. With the cap plate definition, we want to specify here what is the stiffened member. It's going to be our column. The reference member is going to be our beam. And we want to toggle this to the option farther. And there we have our cap plate applied here to the top of our steel column. Now we want to make some changes here to the material. We'll set this to A36. The thickness will go ahead and leave as we have it set here, but I am going to modify the option here to dimensions and position. And we're going to modify the width here to 8 inches. The height is going to be 7.5 inches. And we do want to set a small vertical offset to negative 0.25 inches. So we see everything update graphically here. Now, finally, we just want to set the throat thickness of our welds that's connecting the cap plate here to our column. So we'll go ahead and modify the throat thickness to 0.133 inches. We hit our down arrow key and that F8 to go ahead and make those modifications to the rest of the weld elements. So turning now to our end plate, we can see that the end plate needs some geometry modifications as well. So for this one, we want to modify the thickness to 0.5 inches. And I'm going to, again, select the dimensions and positions option here. I'm going to set the width to 7 inches. The height is going to be 11.5 inches. the vertical offset and horizontal offset will be set to 0. So although it's bringing in these components from the library, we're most likely always going to need to make geometry changes unless we have identical members as what the library option does. So for this one, again, making changes to that end plate, this looks quite a bit better. So our bolts are going to be A325, and we're going to modify this to 1/2 inch diameter. Now we want to have 2 rows in the horizontal direction, but I do want to modify here the spacing. So the first spacing input is going to be from the edge of the plate on the left to the center of my bolt here in my first row. And for this one, we're going to set this to 1.5 inches. I hit my space bar, and then I set 4 inches for the space of our bolt to our second bolt on the other side. I hit enter, and the program will adjust those. Now, I only want to have 3 bolts here vertically, and I'm going to set the spacing here from the top of the plate to the center of the first bolt in the vertical direction to 1.75. I hit the space on my keyboard. My second spacing from the first bolt to the second bolt is going to be 2.5 inches. I hit the space bar, and my final spacing is going to be 4 inches, and I hit enter. And now the layout of those bolts looks quite a bit better. If we want to specify pre-tension bolts or that slip critical connection, we can go ahead and do so here with this checkbox. Maybe the shear plane is not located within the thread. We can go ahead and turn this off. And finally, we have our welds. We want to modify the throat thickness here to 0.133 inches, and we hit our F8 key to apply that to all welds. So that looks good, but let us move on to our additional components here. The member cut, we actually don't need this, so I'm going to delete this one altogether as well. And for our haunch, we want to specify this A36 material. That's great. I'm going to modify the thickness to 0.375 inches. And I also want to specify the width here to 8 inches and modify the height to 4 inches. So that should look quite a bit better, intersecting with that end plate there. As far as the flange for my haunch, again, we want to modify the thickness to 0.375 inches, and then we're going to modify here the width to 4 inches. And yet again, we have all of our welds, so we'll specify this throat thickness at 0.133 inches, and hitting F8 all the way down this row, we can specify that same length for the other weld types. Now, finally, we have our stiffeners. So we have our first stiffener located on the left. Looks fairly good, but we need to move this further up in the column. We'll also make changes here to the thickness. We'll set this at 0.375 inches. And I want to set the offset location. So this is measured from the top of this column down to the center of the stiffener. We'll go ahead and modify this one to 4.5 inches. And now we see that looks quite a bit better. We can also modify the chamfer for our weld axis here to something like 0.75 inches. And similar to our other components, we'll modify the welds to 0.133 for our throat thickness, hitting the F8 key yet again. Okay, so we finally have this last stiffener to take care of. Really exact same concept here. We want to modify the thickness to 0.375 inches. We also want to modify the offset here measured from the left edge of the beam to something more like 13 inches. So that will bring it over to a much better location here. And then looking at our chamfer thickness here for that weld axis as well, 0.75, and modifying our throat thickness for our welds to 0.133 and our F8 key. So this connection is done, and you could save this here to your user-defined template. So this will go into that library that we just saw. You could give it a name, a description, and you can always access this exact same connection with these same components for any other future RFEM models. So the fourth tab, we really haven't visited yet. This is the plausibility check. So this is a nice check when you are creating your connections. The program will warn you of any errors. So if you have overlapping members, or if we left this haunch here kind of connected directly to the member instead of the end plate, we would see those errors listed. But also under this tab is that new ability to save this connection as a DXF. So we could save this in the lower right-hand corner. If we wanted to take a look at what it looks like imported into something like AutoCAD, you can see all of the various line elements shown here. So again, that was a new feature added just this week. You also can save that submodel within this dialog box. So I showed you previously how to do that with example number 1 after we solve for the connection, but you can certainly save the submodel before running the results with our option available here. Okay, so once we have this connection completed, we can actually see it applied globally to the structure. So we can zoom in here and we can take a look at the connection components defined at all 4 locations. So we will jump here to the results. And of course, we have carried out the steel joint design. And very similar to example number 1, we can visit the stress strain analysis to view the various design checks of the plates, the bolts, the welds. But we also have an additional option in this dropdown called the stiffness analysis, because if you remember, we had told the program to carry out the stiffness calculations of this particular connection. And what we see within this dialog box for the column is the true stiffness properties in kip per feet. You can see here for the axial stiffness in the positive and negative direction, as well as kip feet per radians for our rotational stiffness. So even more so, if I turn off the display of this connection and we go back into RFEM thinking more about the member design. If I double click on this column, you remember when we were reviewing the model, I said that I didn't apply any hinges to these column elements. Well, now you can see that this is automatically grayed out and turned on because the steel joints add-on has exported out the stiffness of this particular connection to the member itself. And we take a look at this for translation and rotation. These are now set to the nonlinearity type diagram, and we can see this information directly input in here from the steel joints add-on for both our axial stiffness, but also our rotational stiffness. So now if we were to carry out the design again of our steel members, so not looking at the connections, but the steel members themselves, and we take a look at our design ratios. Remember I had mentioned we're very sensitive to serviceability checks possibly for this steel platform. We now see that our deflection checks are actually failing. So by taking into account the true stiffness of this moment connection from the steel joints add-on, we can consider that with the global model in RFEM. We carry out the design checks of the AISC, and now we see this failing design ratio flagging us, okay, we probably want to make some modifications here to our structure if it is sensitive to those deflections. All right, so we will go back to the PowerPoint here to close out today's presentation. I have listed a few additional new features here, again, that you can review within this PowerPoint. We just simply didn't have time to go over all of them today, but maybe one worth mentioning is this first one of adding dimensions. So if you are working in the components that we just saw with these examples today, you can right click in the white space here to add dimensions graphically. So this might be user friendly in just determining offsets and things like that, placement of anchors and components to help you out. As far as steel joints future development, so I have a long list here because we're always actively working to make the program better for you guys. Several are concurrently going on at once here, and maybe a few just worth mentioning are anchors with anchor heads. You can see that over here on the right-hand side. We're also working on topics like hooked anchors. So maybe you have a 90-degree turn here or 180. That will also be possible to define in the future. Also members with solid sections. So we want the ability in our submodel to define those solid elements like a round or rectangular bar. For our Canadian users, we definitely know it's really important to get the Canadian standard in the steel joints add-on as well. So we're actively working on that to bring that to you guys as well. So we'll certainly keep you updated. Another big topic is the standalone solution. So we also recognize that not everybody has the interest to design the full global model, although that is an advantage. You certainly can do just individual connections by modeling a short member and applying member end forces directly to that element. But we do want to develop here a true standalone solution for connection design, not requiring you necessarily to model the full 3D structure. So again, we'll continue to keep you updated as we carry through with these development features. So if you liked what you saw today with the steel joints, the steel connection design, steel member design, or any other capabilities, and would like to speak with our sales team, you're welcome to contact us here with the QR code. You can visit our website at delubal.com. Would love to coordinate that meeting with you further and get you set up with the trial version. So we will have many more upcoming webinars. You can register at delubal.com under support and learning webinars. As most of you know, I tend to send out a reminder email about a week before these take place, so you can register through the email as well. We do have a webinar occurring already next week on Tuesday about our API within RFEM 6. So that's at 10 a.m. Eastern. Again, next week on Tuesday. Would love to see you guys there. You can register directly on our website. PDH certificates will automatically be emailed to all participants who were here for the full presentation today. So that is a requirement of the states that we are pre-approved providers, that you are here for the full 60-minute duration in order to receive that PDH. If you watched with a colleague or you watch in a conference type setting and you yourself did not register for this GoToWebinar, but you are wanting that PDH, you will need to send us an email request here to info-us@delubal.com. Let us know who you watched it with, and we will be happy to send you that PDH. Again, sending that request to info-us@delubal.com. And with that said, I want to thank everyone for attending. And as always, we hope to see you at the next presentation.